In this video, I will briefly define types of numerical quantity. I will define precision and accuracy and use examples to illustrate the difference between precision and accuracy. The next topic I will discuss is determining uncertainty in a measurement, and the last topic will be rules for recording measurement. Okay, so let's look at the first topic, numerical quantity. Numerical quantity can be one of two ways, either as an exact number or as a result of some measurement. Examples for exact numbers are the numbers that you can count. For example, 7 days in a week. 7 is exact number because number of days in a week is universally defined to be 7, and this number has no uncertainty or doubt in it. Similarly, the number of coins in your pocket is also an exact number because you can't have partial coins. The second type of numerical quantity is a result of some measurement. For example, measurement of a diameter of a coin, or height of a building, or weight of a coin, etc. Now, let's look at some examples and determine types of numerical quantity in following numbers. Here we have number of coins. By definition, something that you can count are exact number. So this will be the exact number. Second we have is diameter of a coin, which looks like a result of some measurement. So this is a measurement. And then radius of a coin and mass of a coin, all these three numbers are the result of measurement. So they are the measured type of quantity numbers. Let's look at our next topic, which is precision and accuracy. Precision refers to how close a series of measurements are to each other. That means if you have a series or several measurements on same object and they are very similar to each other, then that set of measurement is precise. Accuracy, on the other hand, refers to how close the measured result is to the true value. To understand these two definitions, accuracy and precision, let's look at this example. In this example, we have divided 6 students in 2 teams. We have Team A and Team B. And each student in these teams has to measure the diameter of a coin once. The result of their measurements are on the screen, and we know that the true diameter of this coin is 2.5 centimeter. One thing that we can do with these type of repeated measurements is to take average. So the average of Team A's result is 2.5 centimeter and Team B's result is 2.2 centimeter. And you know how to find the average. You will be adding these three measurements and then divide them by the total number of measurements that you have, which is 3 in this case. So now we can use these numbers or the data that we have on the screen to understand precision and accuracy. Precision refers to closeliness of a series of measurements on the same object to one another. In our example, this Team B was precise because its measurements were all the same and thus as close to one another as possible. Another point to know about precision is that the term precision has meaning only when there are 2 or more measurements. Only then you will be able to compare to each other how close they are. So if there is a single measurement, we cannot speak of precision for that measurement. Team A, you can see, was not precise because their measurements were all over the place, ranging from 2.0 to 3.0. Now let's look at their average. The average measurement, you can see Team A's measurement is the average result is 2.5, and the true result is also 2.5. So we can say that team A's average diameter is close to the true diameter, and then team B's average. Unlike precision, the term accuracy can be applied if just a single measurement is made. So this third member of team A have made most accurate single measurement. Now, if we have to summarize this result, we can say that team B's result is more precise but not accurate, whereas team A's result is accurate but not precise. Let's look at another example. In this example, I have a dartboard. The bullseye in this dartboard represents the target or accuracy. In this left dartboard, all the arrows are inside the dartboard, so they are accurate. And since they are very close to each other, so they are precise as well. Now the dartboard in the middle, all arrows are very close to each other, so they are precise, but they didn't hit the bullseye, so they are not accurate. Now this far right dartboard is not accurate because none of the arrow hit the bullseye, and they are not precise as well because they just spread out all over the dartboard. So this is not precise and not accurate. Now, the goal of a chemist that you need to remember, the goal of a chemist or scientist is to take the measurements, those are both accurate and precise. They shouldn't be away from accuracy, and they shouldn't be spreading all over the place. We have two students count the grain of uncooked rice in a small cup. This measurement was repeated 4 times by both the students with the following results. Mike's results are 256, 263, 262, and 266. And Ike's results are 250, 242, 270, and 278. The actual number of grain is 260. We have to find which student is more accurate and which student is more precise. And remember, in order to find precision, we have to find how close these measurements are to each other. And in order to find accuracy, we have to find the average of these results and then compare that average with the true number or the true result that we have. Okay, so let's start with which result is more precise. So for precision, we have to find the range of Mike's result and Ike's result. The range of Mike's result is 266 minus 256, and it is 10. And for Ike, it is 278 minus 242, 36. So based on these two numbers, if you compare, the smaller the range, more precise that result. So Mike's result is more precise and Ike's result is not precise. Now the next is to find which result is more accurate. We have to find the average of Mike's result and Ike's result. To find average, we added all these measurements and divided them by 4. Same thing we did for Ike. We added all these and divided them by 4. Their answer or their average is 262 for Mike and 260 for Ike. So if you compare these two numbers with the accurate or actual number of grain, you will know that Ike is more accurate. So Ike's result is more accurate, but Mike's result is more precise. And remember that the goal of a scientist or a chemist is to ensure that the reading or the measurements that we are taking are both accurate and precise. Okay. Let's move on to our next topic, which is how to record a measurement using different measuring devices. The rule here is while taking measurement, we always take one estimated digit. And this estimated digit is the last digit. The digit prior to this estimated digit is always a mark on the device. And this estimate actually helps scientists to determine the precision of a measuring device. Let's look at this ruler that we have on the screen. And we have to see how to record the length of this crayon based on the lines that we have on this ruler. All measurements are made by determining the marks on the measuring device and then estimating one place beyond the precision of those marks. So this ruler is a centimeter ruler where each line is worth 10 centimeter. You have 0 centimeter here and then you have 10 centimeter. So when you record the length of this crayon, you will estimate it to the ones place. And the length of the crayon is longer than 0 centimeter, but less than 10 centimeter. So an appropriate reading for this crayon would be either 4 or 5 centimeter. Could you say that the reading of this crayon or the length of this crayon can be 5.5 centimeter? And the answer is no, because tenths place is not within the ability of this ruler. Now let's look at another example. Okay. In this ruler, and before we start taking the measurement, remember that all measurements are made by determining the marks on the measuring device and then estimating one place beyond the precision of those marks. Now, this centimeter ruler has lines, and each line is worth 1 centimeter. So this is your 1 centimeter, 2 centimeter, 3 centimeter. So when you record the length of crayon using this ruler, you will be estimating it to 10th place. And the length of this crayon is longer than 4 centimeter, but less than 5 centimeter. So the appropriate reading for this crayon would be somewhere 4.2 centimeter to 4.3 centimeter. In this measurement, 4 is the known number, and this 2 or this 3, these are the last digit or the estimated digit. Now, for this ruler, is it possible to take a reading up to 100th place? Can you take it as 4.35? And answer again is no, because this 100th place is not within the ability of measuring device. The ruler is divided in centimeters, so this 4 is your known digit from the ruler, and after that you will take one estimate, and that estimate is in the tenths column. If the measured object is exactly on the line, like in this example, then you need to add a 0 at the end. So if you are taking the measurement of this crayon, which is exactly at 4 centimeter, the reading that I will take here will be 4.0 centimeter. Okay, let's move to the next example. In this example, the centimeter ruler is divided in 0.1 centimeter, like each line worth 0.1 centimeter. So when you record the length of this crayon using this ruler, you will estimate it to the 100th place. So the length of this crayon will be 4.24 or 4.25. 4.2 is my known digit, my certain numbers that I took from the ruler, and 4 or 5, these numbers are my estimated numbers. Now again, for this, could you say that it can be 4.254 centimeter? Can you add a thousandths place in here? And the answer is no, it is not possible, because this thousandths place is not within the ability. The key to remember from this topic is that all measurements are made by determining the marks on the measuring device and then estimating one place beyond the precision of those marks. Our next topic is uncertainty in a measurement. Counting is usually exact, but measurement on the other hand are subject to error. In this topic, we will identify where the uncertainty lies in a measurement and how to determine the amount of uncertainty. So where does uncertainty lies in a measurement? It is in the last digit of the measurement. You are looking at the measurement 2.46. In this measurement, the last digit 6 is the estimated or uncertain digit. The remaining digits that you have on the left are certain digits. We have many examples after a couple of slides that will give you more idea about how to determine the uncertain digit and how to determine the quantity or exact amount of the uncertainty. Okay. In this slide, we will learn how to calculate exact amount of uncertainty. To calculate the exact amount of uncertainty, we need to identify the amount of uncertain digit, which is the last digit of the measurement. And then we put 1 in that column and zeros, 1 0 or more, for the rest of the columns. For example, let's do one example to calculate the exact amount of uncertainty. So example we are taking is 2.46. First step is to determine the uncertain digit, which is 6 or the last digit of the measurement. Next, we are going to add plus minus, and I will explain in a bit what this plus minus mean. After this plus minus, we will put 1 in the uncertain digit, and this uncertain digit is the 100th place. So I have 1 in the 100th place, and for the rest of the digits, I will just add 0. So 0 will go in the 10th place, and 0 will go here in the 1st place as well. So uncertainty in 2.46 will be plus minus 0.01. And the way we write the uncertainty in a measurement is this whole line that we have, like 2.46 plus minus 0.01 will be your answer. Now, to explain what this plus minus 1 means, because this last digit is the uncertain and the uncertainty is with this plus minus, it means that the true value is somewhere between 2.45 to 2.47. Now, this is just to explain what this plus minus mean, but you don't have to do this calculation every time you are finding the uncertainty. Your answer will only be up to this. In this slide, we have many examples, and let's see how to express uncertainty in these numbers. Okay, so the first example that I have is 58.32. So in this example, the last digit is the hundredths place. So to show uncertainty here, it will be plus minus 0.01. I have 1 in the last digit and zeros for the rest of the digits. The second example, the last digit is ones column. So uncertainty here will be plus minus 1. In C, we have last digit here. 9 is our last digit. So we are going to put 1 here. Okay. In D, the last digit is tens column or tens digit. So uncertainty for this will be 0.1. And in E, uncertainty will be in hundredths column, and for F, it will be in ones column. Okay, that is how we determine the amount of uncertainty.